Ugh. As promised, today we are going to investigate why lemons are sour, as well as why soap is so slippery. Hey, come back here, you little... While I retrieve the slippery soap, let's begin our study of acids, bases, and salts. Whoa.
In this lesson, you will classify compounds as acids, bases, and salts based on the Arrhenius definition. Classify compounds as acids or bases based on an operational definition, and name acids, bases, and salts.
Think way back to the beginning of this course. What is it that we are trying to do in chemistry?
Study matter.
Exactly. And you will remember that we quickly discovered that we needed some ways to classify matter, or we were going to feel really overwhelmed. What are some of the ways we have classified matter thus far in our studies?
First, we classified matter as elements, mixtures, and compounds.
We classified the mixtures as homogeneous and heterogeneous.
Very good. Anything else?
We classified the compounds as ionic or covalent.
We've also used the terms molecular and organic.
And don't forget solids, liquids, or gases, or suspensions, solutions, and colloids.
I can tell you all have been listening because you are exactly right. We have classified matter in many ways so far in our journey through the world of chemistry. This unit is no exception. Many of the compounds we have studied thus far can be classified as acids, bases, and salts. Let's look first at how we can make these classifications based strictly on the elements and ions making up the compounds.
All acids contain a hydrogen atom, which is stripped of its proton when the acid is placed in solution with water. The protons given up by the acid combine with water molecules to form positive hydronium ions. All bases contain negatively charged hydroxide ions. When a base, such as sodium hydroxide, is added to water, the number of negative hydroxide ions in the water increases. As the hydroxide ions dissociate from whatever positively charged ion, in this case sodium, they were combined with.
So, acids contain hydrogen ions and bases contain hydroxide ions. I think you should get that information into your notes.
Svante Arrhenius was a Swedish chemist who studied acids and bases in the late 1800s. He had a very simple theory regarding acids and bases. Arrhenius believed that acids would ionize in water, releasing hydrogen ions, and bases would ionize in water, releasing hydroxide ions. For example, HNO3 is nitric acid, a polar molecule. When nitric acid reacts with water, the hydrogen ions are attracted to the polar water molecules. This causes the dissociation that releases the hydrogen ions into the water. Sodium hydroxide, or NaOH, on the other hand, is a base that contains the hydroxide ion, OH with a -1 charge. When sodium hydroxide reacts with water, it dissociates, releasing the hydroxide ion into the water. According to Arrhenius, an ionic compound that produces neither the hydrogen ion nor the hydroxide ion is called a salt.
Let's use this information to start filling in the chart on our note-taking guide. According to the Arrhenius definition, a compound that begins with hydrogen, such as HNO3, is classified as an acid. A compound that ends with the hydroxide anion, OH, such as NaOH, is classified as a base. And an ionic compound which contains neither of these, such as NaCl, is classified as a salt.
On your note-taking guide, jot down each of the following examples and write an A for acid, B for base, and an S for salt. Are you ready? Here we go. H2SO4, HCl, NH4OH, KNO3, KOH, HC2H3O2.
Now, my students are going to help you check your work.
H2SO4 is an acid because it starts with an H.
HCl is also an acid.
NH4OH is a base because it ends with the hydroxide ion.
KNO3 is a salt according to the Arrhenius definition.
KOH is a base, while HC2H3O2 is an acid.
That's pretty easy stuff, huh? However, I should mention that Arrhenius wasn't the only chemist who came up with a definition for classifying acids and bases. T.M. Lowry and J.N. Bronsted, as well as Gilbert Lewis, proposed new definitions for classifying acids and bases. These new definitions did not exclude any of the compounds that would be classified as acids or bases, according to the Arrhenius definition. They only expanded the definition to include more compounds. The Arrhenius definition is the classical definition that is most commonly used, and it is the one we will use in our study. In addition to the Arrhenius definition, we will also use what we call an operational definition to classify acids and bases. An operational definition is simply a list of properties that can be used to make a classification. My students are going to help you begin to develop an operational definition to classify acids and bases.
The students are working with an aqueous solution of each of the compounds listed in your note-taking guide. The first property they're going to test is whether or not each solution reacts with a strip of magnesium. If the solution reacts, simply put an R in the space provided on your note-taking guide. If the solution does not react, write NR in the space provided. The first solution being tested is HNO3. The student inserts the strip of magnesium and watches for bubbles. Don't forget to record your observation. Next is NaOH. Now the students test NaCl. Next is H2SO4. How about HCl? Next, the students test NH4OH. Now for KNO3. Next is KOH. And finally, HC2H3O2. Now the students are going to test the conductivity of the solutions. You will remember the conductivity testers from previous lessons. If the solution conducts electricity, write C. If the solution does not conduct electricity, write NC. Here goes. The first solution being tested is HNO3. The students insert the conductivity tester and watch for it to light up. Don't forget to record your observation. Next is NaOH. Now the students test NaCl. Next is H2SO4. How about HCl? Next, the students test NH4OH. Now for KNO3. Next is KOH. And finally, HC2H3O2.
Excellent! Let's see if we can come up with that operational definition. Looking at your chart, can you list any properties that are characteristic of acids or bases?
Well, all of the acids on our chart reacted with a strip of magnesium.
Very good. Reacting with metals such as magnesium is indeed one of the properties of acids. Anything else?
It seems that all of our solutions conducted electricity to some extent.
Right again. You'll remember from our last unit that compounds that conduct electricity in an aqueous solution are called electrolytes. It's true that acids and bases as well as salts are electrolytes. Now, let me give you a hint to see if you can determine any other properties to add to our operational definition. Remember my lemon? It contains citric acid. And my bar of soap contains a base. Got any ideas?
Well, you seem to think that lemon tasted sour. I wonder if all acids taste sour.
Well, if taste is what we're talking about, I'd have to say that bases taste bitter. Well, not that I've had my mouth washed out with soap or anything.
I wonder if the slipperiness of the soap is another characteristic of all bases.
Wow, I can't get anything past you guys. Yes, all acids have a sour taste. Yeah. And all bases have a bitter taste. No. Also, bases tend to feel very slippery. Just as a safety reminder, I didn't let my students discover these properties by tasting and touching our non-solutions because tasting and touching aren't allowed in the lab. Let's go ahead and put our operational definition into your notes.
The Arrhenius definition of an acid. It is a compound that will dissociate in water to produce hydrogen ions. Let's look at an operational definition of acids. One characteristic of acids is that they have a sour taste. Acids also react with metals to produce hydrogen gas. A third property to add to our definition is that acids are electrolytes, so their aqueous solutions conduct electricity. Two additional properties of acids will be looked at more closely in the next couple of programs. First, acids turn acid-base indicators different colors. Second, acids react with bases to produce a salt and water. The Arrhenius definition of a base. It is a compound that ionizes in water to produce hydroxide ions. Now let's look at the properties of bases that make up our operational definition. Bases have a bitter taste. Bases feel slippery to the touch. Bases are electrolytes, so their aqueous solutions conduct electricity. The following two properties of bases will also be studied more in the next couple of programs. 1. Bases turn acid-base indicators different colors. And 2. Bases react with acids to produce a salt and water.
Wow, you've already learned so much today. You can classify a compound as an acid, base, or salt based on its chemical formula. You can also classify a compound as an acid or base based on its properties. The last thing we want to do is learn how to name acids, bases, and salts. We'll take a look at bases and salts first because you already know how to name them.
Because bases and salts are simply ionic compounds, you follow the standard rules for naming ionic compounds. For example, NaOH would be named sodium hydroxide, and CaCl2 would be named calcium chloride.
Now, we'll focus on naming acids. This is a little different than what we've done in the past. The first thing you have to do is determine if the acid is binary or ternary.
A binary acid consists of only two elements, with the first one being hydrogen. The name of a binary acid is hydroblankic acid, with the blank being the root word of the second element. For example, HCl is a binary acid because it only has two elements, and the first one is hydrogen. The name of this acid is hydrochloric acid. A ternary acid consists of 3 elements, with the first one being hydrogen and the other 2 elements making up a polyatomic ion. To name a ternary acid, you do not use the prefix hydro. You simply change the ending of the polyatomic ion's name and add the word acid. If the polyatomic ion's name ends in ATE, you change it to IC. If the polyatomic ion's name ends in ITE, you change the ending to OUS. For example, H2SO4 and H2SO3 are both ternary acids. The polyatomic ion SO4 has the name sulfate. Since the name of the polyatomic ion ends in ATE, the ending is changed to IC when naming the acid containing this polyatomic ion. So, H2SO4 is called sulfuric acid. The polyatomic ion SO3 has the name sulfite. Since the name of the polyatomic ion ends in ITE, the ending is changed to OUS when naming the acid containing the polyatomic ion. So, H2SO3 is called sulfurous acid.
Here's a great hint for remembering which ending changes to IC and which ending changes to OUS. Think of it this way. If you ate something that didn't agree with you, your stomach would feel ick. Pretty clever, huh? Our first example is H3PO4. Since there are 3 elements involved, it is ternary, and we need to look on our charge chart. PO4 is the phosphate ion. If I ate something bad, I would feel ick. So the acid is called phosphoric acid. If you called it phosphic acid, that would be okay. But chemists change phosphate to phosphoric acid. They also change sulfate to sulfuric acid. There's no reason for it, but that's the English language for you. You'll get used to these 2 names as we go along. Now, let's try HF. Well, since there are only 2 elements, this is a binary acid, and its name is hydro-something-ic acid. Since F is the symbol for fluorine, we write fluor in the blank, and this is hydrofluoric acid. We'll do one more together, and then I'll give you a few to try. Let's figure out the name of HClO2. Since it's ternary, we look on our charge chart and see that the ClO2 ion is the chlorite ion. That means that this acid will be the chlorous acid. Just remember, if it is binary, the name is hydro-something-ic acid. If it is ternary, you change the ending of the polyatomic ion and then add the word acid. Ate goes to ic, and ite goes to us. Now, you try some.
Name each of the following acids. HBr, HNO3, HNO2, and finally HI.
HBr is a binary acid with the name hydrobromic acid.
HNO3 is a ternary acid with the name nitric acid.
HNO2 is a ternary acid with the name nitrous acid.
HI is a binary acid with the name hydroiodic acid.
I'll clean up here. You take your chemistry quiz. Whoop.
Cumulative review question number 1. STP is A, standard temperature and pressure, B, 0 degrees Celsius and 1 atmosphere pressure, C, 0 degrees Celsius and 101.3 kilopascals, D, all of these. Cumulative review question number 2. Which of these statements about dissolving gases in liquid solvents is true? A, increasing the temperature makes gases more soluble. B, increasing the pressure increases the solubility of a gas. C, stirring increases the solubility of a gas in a liquid solvent. Number 1. Which of the following would be classified as an acid according to the Arrhenius definition? A, NaCl. B, CaOH2. C, H2CO3, D, BaBr2. Number 2. Which of the following is not a characteristic of a base? A, turns acid-base indicators different colors. B, feels slippery to the touch. C, tastes sour. D, is an electrolyte. Question number 3. If you came upon an aqueous solution in the lab that reacted with a strip of magnesium, you could make the hypothesis that the compound in this solution is A, an acid, B, a base, C, a salt. Name the following base for question number 4. KOH. A, potassium base. B, hydropotassium base. C, potassium hydroxide. D, hydropotassium hydroxide. And finally, number 5. Name the following acid. H2CO3. A, hydrocarbonic acid. B, carbonic acid. C, carbonous acid. D, hydrocarbonous acid.
Haha, gotcha. Well, so much for our introduction into the study of acids and bases. Bet you're wondering why I have this head of cabbage here. Stay tuned, and you'll find out in our next program.